So hello everyone. Our group is talking about AI-driven maps of the trees outlet forest in sub-Saharan Africa, and we mainly focus on Malawi. The reason we're doing this is because Africa facing a deforestation and degradation over decades, and most of people thinking about degradation is probably thinking about the forest is shrinking its size, the size of the forests, but actually the trees outside forest is also very important, and it brings a lot of ecological and economically important to the people in that area. Um, However, when the trees out of forests are often left uncounted in the previous studies, and counting trees and is estimating the biomass of regions in sub-Saharan Africa is due to the coarsest spatial resolution of the traditional remote sensing images. And Malawi, as a case study, it has very severe land degradation and large pools of trees outside forest, and it has a strong community trees planting initiatives.
That brings us to a research gap that Malawi has no wall-to-wall individual tree map of outside forests and no repeatable record of how they change over time, which makes scattered trees much harder to identify and track from year to year. That's what we set out to cover, and it breaks down into four objectives. First, we download 3-meter imagery covering all of Malawi from each year from 2020 or 2016 to 2025. And then we'll stitch it into wall-to-wall mosaics that feed into our models. From there, we'll generate training labels, which are both hand-drawn and weak labels from a canopy height model. And finally, we'll apply those models to map into individual trees across the country. That leads us into our workflow. As you can see in this image, we grid the whole country into tiles, and for each tile, we pull satellite imagery, which are 4 bands to 8 bands every year from 2016 to 2025. That imagery goes into our deep learning model, which then outputs a tree map for each year. And comparing the earliest and latest maps, we get the change in tree cover over the decade.
Let's talk a little bit about our model architecture. Initially, our inputs are those manual delineations with the tree downloading and imaging process, which Apollo talked about, and Michael will talk about the delineation process afterwards. We also combine that with meta canopy height maps, but we trust these less than we trust our annotations, so we put a coefficient in front of them, which is roughly 0.7, in order to trust to affect our backpropagation updating. We feed these into our convolutional layers, which are going to learn lower resolution features as well as higher semantic level features in the later layers. Then we combine this into a UNet segmentation network, which is going to provide pixel level segmentation for the entire grid, and combine that with a visual transformer, which should be able to help us, which should help the network learn large-scale patterns and global patterns across the entire grid. And then that gives us eventually a pixel-level cover map with a classification for each pixel.
And moving on to the manual delineation part, since we know that AI is data hungry and we need lots of accurate hand training data so that we can make the model much more predictable and accurate. And throughout the project, we have already labeled roughly 80,000 trees across 2016 to 2025. And we believe this is going to be a valuable training set for our model. And after that, we'll also have 15,000 ground truth data to verify if our AI model is accurate or not.
Awesome. And to end us off, I want to show some of the preliminary outputs of our hard work this summer. So here's our early stage results. So here's an example. Obviously, we don't have all 10 years here. We just have 4, 2018, 2020, 2023, and 2025. And here are our inputs. So here's just RGB satellite imagery. For 2018 to 2020, our satellite imagery was 4 bands, and for 2020 and after, it was 8 bands. So you're just seeing RGB right here, but we also have infrared and some other bands here. And here's our preliminary output. So if you zoom in on this, this is where, via semantic segmentation, where our computer vision pipeline predicts where the trees are and where they aren't. So you can see it did a pretty good job on this patch in 2018, around 2.5 million trees in this small area here. Around 2020, you see a couple more trees, and around 2023, a couple less, and then a similar number in 2025. So you can see each color represents one individual tree in the pipeline here. And finally, as an overview of our hard work this summer and our future work, so we've generated over 2,000 mosaics over the 10 years and over the entire area of the country of Malawi. And as Michael mentioned earlier, we drew 80K manual labels. It was hard, meticulous work this summer. And decadal mapping, that means mapping over 10 years, we've completed for 40 out of 200 grids. So we're about 20% done, and we're going to continue the work over the rest of the summer and into the fall. So, and moving on for our future work, we're going to run models for the remaining grids, around 161 remaining grids. And then after developing our map, we're going to analyze changes in tree crowns over time, which we can apply to new ideas like biomass and biodiversity. And we can analyze where the most change is happening and where the most growth is happening, and perhaps present our ideas to the people of Malawi. And then eventually, using this pipeline that we've used for the country of Malawi, we're going to expand to cover more of sub-Saharan Africa, which is a critical area for ecological research over the next couple of decades. So yeah, thanks for listening, and enjoy the rest of the presentations.